All right, let's go over Unit 2, which is Stoichiometry. And this will be quite the refresher because this was our second unit, and I doubt it would be fresh on anyone's mind. All right, so let's start with question 1. Determine the total molar mass of ammonium phosphate, NH4 3PO4. So in order to do this, I usually take my whole thing and segment it into pieces. So if I segment this into pieces, we have NH4, 3, and PO4. Alright, so when we have parentheses, we know that we have to take this 3 on the outside and distribute it to each of the elements that are in the inside. So if you do that, we get, if I enlarge it a little bit, NH4, 3. The 3 goes to the invisible 1 on the N, and the 3 also goes to the 4 on the H. So this gives us, in the end, 3 nitrogens, 3 nitrogens plus 12, because 4 times 3 is 12, 12 hydrogens, and whatever is on PO4. Excuse me. So if PO4 has 1P, we're going to have 1P and 4, since there's a 4 oxygens. This will be the total molar mass. Total molar mass. All right. So N, nitrogen's molar mass, or the number on the periodic table, is going to be 14.01. So 3 times 14.01 plus 12, and then hydrogen's number is 1.01. Phosphorus is 30.97, and oxygen is 16. So 3 times 14.01 added with 12 times 1.01 added with 1 times 30.97 added with 4 times 16 will eventually give you in the end 149.12, and the unit for molar mass is always going to be grams per mole. And that is your final answer. Let's try number 2. If 5.5 moles of calcium carbide, CaC2, reacts with an excess of water, how many moles of acetylene, C2H2, will be produced? And we have an equation. And so we have to remember that using these information given like 5.5 moles, and we're given question mark, so we don't know how many moles of acetylene we need. So I like to write my numbers on this equation. On the equation given here. So we have calcium carbide here. So 5.5 moles of calcium carbide, and we're looking for acetylene, which is here. So I'm going to put a question mark mole for acetylene. So the way we start this is we want to use our dimensional analysis. So we start with whatever we're given always, 5.5 mole CaC2, and then times sign, draw a line. If you remember that, it's pretty catchy, but it gets the job done. And this is the part that's special for stoichiometry. We have to use conversion factors. So on our equation, for every 1 mole of CaC2, there's an imaginary 1 in front. For every 1 mole of CaC2, there's 1 mole of C2H2. So there's also an invisible one there. So our conversion factor is 1 mole CaC2 is equal, or we can put it in fractions, this is a conversion factor, is equal to 1 mole of C2H2. This is our conversion factor for this equation. So conversion factor. And we're going to use this in our dimensional analysis here. So we have moles of CaC2 on top. So our moles of CaC2 has to come on the bottom. So 1 mole CaC2. And these units cancel. Our end goal is to get how many moles of acetylene, C2H2. So we have to put the C2H2 on top. 1 mole C2H2. Okay, now we have these cancel, and we're left with the question mark mole of C2H2. So all we got to do is multiply everything on the top, 5.5 times 1, and then click enter on your calculator and multiply by and then multiply everything on the bottom, and then divide that with the number you got on the top. So 5.5 times 1 is 5.5. Click enter, and then divide it by the multiplication data of the thing on the bottom. So 1 times 1 is 1. So 5.5 divided by 1 is going to be 5.5 still. So 5.5 mole, so moles of C2H2. So the way I would write this is grab your 5.5, mole, MOL, that's the abbreviated version, and then I would put C2H2. And that is your final answer. All right, let's try question 3. So if excess sulfuric acid reacts with the 20 grams of sodium chloride, NaCl, how many grams of sodium sulfate, Na2SO4, are produced? And it gives us all the molar mass down below, which makes our calculation much speedier because we don't need to calculate that. And the way we start this is we want to use our given data to establish what we know and what we want to find. So we're given that we have 20 grams of sodium chloride, NaCl, and we want to find the grams of sodium sulfate, Na2SO4. So we want to put question mark gram. So the way we start this is we always use the given data, the number that we're given first. So 20 grams Na2, so that looks like a 9. 20 grams NaCl, and then we want to use our molar mass to convert this grams into moles. So for every 58.44 grams, that's the molar mass. So every 58.44 grams of NaCl, there is 1 mole of NaCl. All right. Now we have to use our conversion factors. So for every 2 moles of NaCl in our equation, 2 mole NaCl, there's going to be 1 mole, there's an invisible 1 there, 1 mole of Na2SO4. All right, and now we have to convert our moles of Na2SO4 into grams because the question asks for grams of Na2SO4. All right, so for every 1 mole of Na2SO4, we're going to have, if we see here, we have 142.05 grams of Na2SO4. Since our units grams of NaCl cancel here, moles of NaCl cancel here, and moles of Na2SO4 cancel here, we are left with grams of Na2SO4 in the end. So that confirms that we can go ahead and solve. So taking 20 times 1 times 1 times 142.05, click enter, and then divide by whatever's on the bottom. So divide it by 58.44 times 2, and then that will give you, in the end, your answer of 24.3 grams of Na2SO4. That is your final answer. All right, take a look at number 4. When iron rusts, it undergoes a reaction with oxygen to form iron 3 oxide. And we have an equation here. Calculate the volume of oxygen gas at STP that is required to completely react with 52 grams of iron, and it gives us the molar mass of iron to use. All right, let me bring the equation down here real quick so we can label it. So Fe solid and 3O2 gas is going to give us 2Fe2O3 as a solid. All right, so we're given 52 grams of iron. So we have 52 grams of iron. And we're looking for the volume of oxygen gas. So the volume is liters. And we want to know how much, so question mark liters of oxygen gas. All right, so based on this, we always start with our given data and the number that we're given. So 52 grams of iron. And then the molar mass comes into play because we got to convert into moles first in order to use our conversion factor. So for every 55.85 grams of iron, that looks like a 9 again, grams of iron, there is 1 mole of iron. All right, now taking a look at our equation, for every 4 moles of iron, there are 3 moles of oxygen. So for every 4 moles of iron, there is 3 moles of oxygen. All right, and now finally, in order to convert from oxygen moles to liters, we got to use another basic conversion factor, which is for every 1 mole of oxygen, there is 22.4 liters of oxygen, and this applies this liter conversion. The one mole equals 22.4 liters applies to anything. So knowing that, we are good to solve for the liters of oxygen gas because all our units, grams of iron, moles of oxygen cancel, and we're left with liters of oxygen gas. So we take our numbers, multiply all across the top, 52 times 1 times 3 times 22.4, and then divide it by 55.85 times 4, and that gives you in the end 15.64 liters of oxygen gas. That is your final answer. All right, let's move on. Let us try question 5. In a reaction chamber, aluminum is mixed with chlorine to form aluminum chloride. If 3 moles of Al is mixed with 5.3 moles of Cl2, which reactant is the limiting and how much AlCl3 is produced? So in order to determine the limiting and limiting reactant, let's define what a limiting reactant is. So take our blue marker, and the limiting reactant, Lr, is the reactant that is completely used. That is completely used up in a reaction. And so for this, we can easily determine this by taking our two numbers and using dimensional analysis to find the theoretical molar yield of AlCl3. Let's go ahead and do that. So we start off with labeling our units. We have 3 moles of Al. We have 5.3 moles. Actually, I'll do this in a different color. We have, let's do that in red. Just kidding, orange. All right. So we have 5.3 moles of Cl2, and we want to know in the end how many moles of AlCl3 is produced. Let's start off with Al. So for every 3 moles of Al, we have to use our conversion factor from the equation, and we want to go straight to AlCl because we're already in moles. So for every 3 moles of Al in our equation, for every 2 moles of Al, there are 2 moles of AlCl3. 2 moles AlCl3. All right, and now our units for mole cancels, for mole Al cancels, and we're left with moles of AlCl3. So 3 times 2 is 6, divided by 2 is 3. So we have 3 moles AlCl3. And now let's calculate the scenario where chlorine. So we have 5.3 moles Cl2. And for every, look on our equation, for every 3 moles of Cl2, we have 2 moles of AlCl. 2 moles, let's get the line a little bigger. 2 moles of AlCl2, or 3, sorry. All right, and now our units for moles of Cl cancel, and we're left with moles of AlCl3. We can solve. All right, 5.3 times 2 divided by 3 is 3.53 moles of AlCl3. From this point, we can determine the limiting reactants because the limiting reactant is a scenario or the scenario of calculation where the starting number of the element or compound that we worked with is limiting the amount of total moles of what we want to calculate in the end. So 2-AlCl or AlCl itself. So in this scenario, the limiting reactant is going to be aluminum because when we had 3 moles of aluminum, we could only produce 3 moles of AlCl3, while in the scenario we had Cl2, we could produce 3.53 moles of AlCl2. So the limiting reactant, is going to be aluminum Al. And how much AlCl3 is produced? Since we know that the limiting reactant is going to be aluminum, we know that this 3.53 mole yield of AlCl3 is impossible because aluminum is restricting the total amount that you can get in the first place, which is going to be 3 moles of AlCl3. So that is our answer. Aluminum is the limiting reactant, and 3 moles of AlCl3 is the theoretical yield, or the total theoretical amount that you could produce, the total maximum theoretical amount you could produce. Let's take a look at number 6. What mass in grams of copper 2 oxide, CuO, are formed in the decomposition of 6.59 grams of copper 2 hydroxide, CuOH2? So this is quite simple. We just got to recognize that what we're solving for and what we're given. So let's write this equation on the side. CuOH2 is going to decompose into CuO and H2O. So in the beginning, we're given with 6.59 grams of copper 2 hydroxide, 6.592 grams, and we're looking for the mass in grams of copper 2 hydroxide, or copper 2 oxide. So we're looking for grams. We always start with the number we're given, 6.59 grams of CuOH2. Horrible too. 2. And we got to use our molar mass, which is given in this table here. For every 98 grams of CuOH2, we have 1 mole of CuOH2. And so for every 1 mole of CuOH2, we have in our equation, for every 1 mole of CuOH2, we have 1 mole of CuO, 1 mole CuO, and for every 1 mole CuO, we use our molar mass again, we have 80 grams CuO. In the end, our units for cancels, grams of CuOH2 cancel, moles for CuOH2 cancel, moles for CuO cancels, and we're left with grams of CuO. So based on this information, we know that we're good to calculate. 6.59 times 1 times 1 times 80 divided by 98, since there's only ones on the bottom. That will give you in the end your answer of 5.37 grams of CuO. And that is your final answer. All right, question 7, the last question. A student performs a reaction and recovers 0.25 moles of N2O3. The theoretical yield is 0.79 moles of N2O3. What is the percent yield? All right, so the equation for percent yield is going to be actual over the theoretical times 100. All right, so this equation, the equation for percent yield, if you look on the first page of your study guide, it is not given. So you have to memorize this. So the percent yield, you have to memorize that it's the actual over theoretical times 100. All right, so we started off as the theoretical yield. It gives us the theoretical yield, and we only got 0.25 off of it. So we know that this is the actual And this is the theoretical. And so all we got to do is plug it in. 0.25 as actual, theoretical is 0.79 times 100. And if you plug this straight into your calculator, it'll give you decimal. But if you round that to the nearest hundredths place, you will get 31.65%. So that is the theoretical yield. All right, that's it.